So let's take a look at directional derivatives and the gradient vector. Now, given a multivariable function f of x and y and a unit vector which has the components a and b, we can go ahead and find the directional derivative. And so what is the formula? Well, the directional derivative is written as d sub u of f of x comma y, the function. And the reason why it's written like that is because we're trying to find the derivative of the function in the direction of the unit vector. So the formula for that is going to be f sub x evaluated at x comma y times a, the x component of the unit vector, plus f sub y evaluated at x comma y times b, the y component of the unit vector. Now, if you're given a theta value or some angle with the positive x-axis, in order to find the unit vector, the a component is simply going to be the x component, which is cosine of theta, or that angle, and b is going to be the y component, so it's sine of theta. And so that will give you your unit vector. So let's go ahead and find the directional derivative of f at the given point in the direction indicated by the angle theta. So for number one, we have the multivariable function equals the square root of 5x minus 4y. The point given is 4, 1, and the angle theta is negative pi over 6. So once again, the formula for the directional derivative, d sub u, of the multivariable function f of x comma y is going to be equal to f sub x evaluated at the point x comma y times a plus f sub y evaluated at the point x comma y times b. And remember, a and b are the x and y components of the unit vector. So let's go ahead and find the unit vector first. So the unit vector is going to be equal to, well, it's going to have its a and b component. And once again, whenever we're given an angle in terms of theta, we can use the formula. The unit vector is going to equal to, the x component is going to be cosine of theta, and the y component is going to be sine of theta. So if theta is negative pi over 6, the unit vector is going to be equal to cosine of negative pi over 6 for the x component, and then comma sine of negative pi over 6 for the y component. Now, negative pi over 6 is the same thing as 11 pi over 6. So cosine of 11 pi over 6 is going to be square root of 3 over 2, and sine of 11 pi over 6 is going to be negative 1/2. So that is going to be the unit vector. And so once again, keep in mind, square root of 3 over 2, the x component is the a component, and then negative 1/2 is going to be that b component. So now let's go ahead and find f sub x. So f sub x, or in other words, the partial derivative of the function with respect to x, is going to be equal to, now x is going to be the variable, y is going to be the constant. So I can rewrite 5x minus 4y as 5x minus 4y to the 1/2 power. So now I can use a chain rule. So we bring the power down when we derive, keep the inside function the same, subtract the power by 1, so 1/2 minus 1 is negative 1/2, and then multiply by the derivative of the inside function. Since we're deriving the variable x and y is a constant, the derivative of 5x is 5, and the derivative of negative 4y is 0. So we're going to multiply by 5. So when I simplify here, I can bring the exponent to the denominator, and so we'll get 5 over 2 times 5x minus 4y to the 1/2. And so now I need to evaluate f sub x at the point xy. So the point is at 4, 1. So let's go ahead and evaluate f sub x at the x value of 4 and the y value of 1. So when I do that, we get 5 on the numerator over 2 times, 5 times 4 is 20, 20 minus 4 is 16, so we get 16 to the 1/2. Square root of 16, or 16 to the 1/2 is 4, 4 times 2 is 8, so we get 5 over 8. So now let's go ahead and find the partial derivative of f with respect to y. So this time, y is going to be treated as the variable, x is the constant. So the first step is the same, where we take the derivative of the outside function. So we use the chain rule here, we get 1/2 times 5x minus 4y to the negative 1/2. And then we can go ahead and multiply by the derivative of the inside function. So if y is the variable, the derivative of 5x is 0, the derivative of negative 4y is negative 4. So notice 4 divided by 2 is 2, so we'll get negative 2 up top over, we can bring the exponent down, so we get 5x minus 4y to the 1/2 power. And so now I need to evaluate f sub y at the point 4, 1. So if I go ahead and evaluate it at the x value of 4, the y value of 1, we'll get negative 2 over, now if I plug in 4 for x, 1 for y, we'll get 20 minus 4, which is 16. 16 to the 1/2 is 4. So negative 2 over 4 will give us negative 1/2. So now we can plug everything into the formula. So the directional derivative of the function is going to be equal to the partial derivative of f with respect to x evaluated at the point, which we found to be 5 over 8, times a, which is the x component of the unit vector, so square root of 3 over 2, plus the partial derivative of f with respect to y evaluated at the point 4, 1, which we found to be negative 1/2, times b, or the y component of the unit vector, which is negative 1/2 as well. So when I simplify, we will get 5 times the square root of 3 over 16 plus 1/4. And so that's the final answer. Now the next set of questions are going to be about gradient vectors. So gradient vectors are written like so. So you have an upside down triangle of the function f of x and y. And so the formula for the gradient vector, notice it is a vector. So the formula, or the x component, is going to be f sub x of x and y. So the partial derivative of f with respect to x. And the y component is going to be f sub y, or the partial derivative of f with respect to y. And so it can also be written as in this form here, partial derivative of f with respect to x times I, and then plus the partial derivative of f with respect to y times j, because I is associated with the x component, j is associated once again with the y component. So for these next set of problems, we have to find the gradient vector. For b, we have to evaluate the gradient at the given point p, and then we have to find the rate of change of f at p in the direction of the vector u. Now don't let letter C confuse you, because the rate of change is the derivative, and we're finding it at the direction of the vector u, or the unit vector. So basically we're finding, once again, the directional derivative. So for number 1, f of x and y equals 5x squared, or 5xy squared, minus 4x cubed y. The point is at 1, 2, and this time a unit vector is already given to us. It's 5 over 13 and 12 over 13. So once again, the formula for the gradient vector of f is going to be equal to, once again, in component form because it's a vector, the partial derivative of f with respect to x evaluated at the point, comma, the partial derivative of f with respect to y evaluated at the point. So let's go ahead and first find f sub x. So f sub x, now x is going to be the variable, everything else is a constant. So the partial derivative of 5xy squared, if we're deriving with respect to x, is going to be 5y squared minus partial derivative of 4x cubed y, which is going to be 12x squared y. And so now if we were to find f sub y, with the partial derivative of f with respect to y, treating y as the variable and everything else as a constant, the derivative of 5xy squared is going to be 10xy minus the derivative of 4x cubed y. And so the derivative of that is just going to be 4x cubed. And so if we were to write the gradient vector here, the gradient vector in its component form is going to be equal to the x component, which is f sub x, which we have found to be 5y squared minus 12x squared y, comma, the y component, or f sub y, which we have found to be 10xy minus 4x cubed. So now for letter B, or for part B, we need to evaluate the gradient at the point P. So the point is 1, 2, so let's go ahead and evaluate the vector at the x value of 1 and the y value of 2. So on the x component of the vector, we get 5y squared, so 5 times 2 squared, 5 times 4 is 20, minus 12 times 1 squared, which is 1, times y, which is 2, comma, 10 times x, which is 1, times y, which is 2, so 10 times 2, minus 4x cubed, so basically 4. So then we get 20 minus 24, which is negative 4, and then 20 minus 4, which is 16. So So that is going to be the gradient vector evaluated at the point 1, 2. Now for the last part, as mentioned before, we need to find the rate of change or the directional derivative. Now there's another formula for the directional derivative, and so the formula d sub u of x, f of x comma y, is going to be equal to the dot product of the gradient vector f evaluated at a certain point, just like what we did. So the dot product of that and the unit vector, u, which is already given to us. So if we go ahead and take the dot product of the gradient vector and the unit vector, remember in the dot product we're going to multiply similar components. So the x components will multiply, so negative 4 times 5 over 13 is negative 20 over 13, plus, and then we multiply the y components together. So 16 times 12 over 13. And so that will give us 192 over 13. So if we go ahead and add those two fractions, we'll get 172 over 13 as the directional derivative. So for number 2, we have f of x, y, z equals x times e raised to the power of 2yz. The point is at 302, and the unit vector given to us is 2/3, negative 2/3, and 1/3. So notice we have three variables this time, x, y, and z. So the formula for the gradient of f has the same structure, we just have to add that z component. So it's going to be equal to, the x component is going to be f sub x, comma, f sub y, comma, and then we have to add that f sub z, all evaluated at the point x, y, z. So let's go ahead and first find f sub x. So f sub x is going to be equal to, now x is going to be the variable, everything else is a constant. So the derivative of x times e to the 2yz is just e to the 2yz. Now f sub y, if y is the variable, everything else is a constant, remember the derivative of e to the raised to some function u is going to be equal to e to the u times u prime. So the derivative of this is going to be x times e to the inside function, which is 2yz, times the derivative of that inside function. And so if we're deriving with respect to y, then the derivative is just going to be 2z. So then I can rewrite it as 2xz times e to the 2yz. Now let's find the partial derivative of f with respect to z. So now if z is the variable that we derive, it's going to be the same process here. We have x times e to the 2yz times the derivative of the inside. This time we're deriving z, so we get 2y as the derivative. So then I can rewrite it as 2 times x times y times e to the 2yz. So in this case, the gradient vector is going to be equal to the x component, so f sub x, which is e to the 2yz, comma the y component, which is 2xz e to the 2yz, comma the z component, 2xy times e to the 2yz. So now let's go ahead and evaluate the gradient at the point P. So the point given to us is 302. So if I go ahead and evaluate it, we get e raised to the power of 2 times 0 times 2. So obviously e to the 0 is 1, so we can just go ahead and say e to the 0, comma, now we have 2 times x times z, so 2 times 3 is 6, times 2 is 12, e to the 0, since the y value is 0, and we always plug in y for all three of these. And then we have comma, 2 times x times y, so y value is 0, so we have 0 times e to the 0, which is also going to give us 0. So if I simplify, e to the 0 is 1, 12 e to the 0 is 12, and 0 is obviously 0. So that is going to be the gradient vector evaluated at the point 302. So now in order to find the rate of change of the directional derivative, we just need to take the dot product of the gradient vector and the unit vector. So once again, in order to take the dot product, we're going to multiply similar components. So 2/3 times 1 is 2/3, plus the y components being multiplied. So we get negative 24 over 3. And then plus, well, if you multiply 0 times anything, we'll get 0 there. So our final answer is going to be negative 22 over 3. So for these next set of problems, we need to find the directional derivative of the function at the given point in the direction of the vector v. So for number 1, f of x and y equals 1 plus 2x times the square root of y. The given point is 3, 4, and the given vector is 4, negative 3. So once again, for the directional derivative, let's go ahead and first find f sub x. So x is going to be the variable, everything else is a constant. So the derivative of 1 is 0. The derivative of 2x times the square root of y is just 2 times the square root of y. And so let's go ahead and evaluate it at the point 3, 4, the point that is given to us. So with the x value of 3, y value of 4, notice there is no x value, so we can just cross out that. But the y value is 4, so 2 times the square root of 4, or 2 times 2 will give us 4. So now let's go ahead and find f sub y. So if y is the variable and x is the constant, derivative of 1 is 0, and derivative of 2x times the square root of y is going to be 2x times the derivative of the square root of y, which is 1 over 2 times the square root of y. So notice the 2's will cancel, so we're left with x over the square root of y. So now let's go ahead and evaluate it at the point 3, 4. So we'll get the x value of 3, so we get 3 over square root of 4, which is 2. So we get 3 halves. So once again, in order to find the directional derivative, we also need the unit vector, which has the components a and b. We are given, notice, a vector, but not the unit vector. So once again, in order to find the unit vector of, let's say, vector v, we need to take the vector's components and divide it by the magnitude of vector v. So since we already have vector v, let's find what the magnitude is. So the magnitude of vector v is going to be the square root of the x component squared, so 4 squared is 16, plus the y squared, or the y component squared, which is 9. 16 plus 9 is 25, and the square root of 25 is 5. So basically, in order to find the unit vector, we're going to take the components, so 4, negative 3, and then divide them by the magnitude, which is 5. So I can rewrite it. If I divide each of the components by 5, I can rewrite it as 4/5 and negative 3/5. So the formula for the directional derivative, once again, d sub u of f of x comma y is going to be equal to f sub x, evaluated at the point, so we got 4 for that, times a, or the x component of the unit vector, which is 4/5, plus f sub y, evaluated at the point, so we got 3 halves, times b, or the y component of the unit vector, negative 3/5. So 4 times 4/5 is 16 over 5, and then I can bring that negative out front, so we'll get negative 9 over 10. So I can find common denominators here. 16 over 5 I can rewrite as 32 over 10, and so 32 over 10 minus 9 over 10 gives me 23 over 10. So for number 2, we have g of s and t equals s squared times e to the t. The point is at 2, 0, and the vector is I plus j. So realize that instead of f of x and y, we have g of s and t, and so we basically treat it the same way. So instead of finding f sub x, let's go ahead and first find the partial derivative of the function g with respect to s. So in this case, s is the variable, t is going to be a constant, so the derivative is 2s times e to the t. And so if we evaluate it at the point 2, 0, then we'll get 2 times 2, which is 4, times e to the 0, which is 1, so 4 times 1 is 4. So now let's find the partial derivative of g with respect to the other variable, t. So this time t is going to be the variable, s is a constant, so the derivative is simply just s squared times e to the t. So now let's evaluate it at 2, 0. And so we'll get 2 squared, which is 4, times e to the 0, 1. 1 times 4 still gives us a value of 4. And so finding the unit vector here, we have the vector v. So if we write it in component form, we could also write vector v as 1, 1. Since the x component is 1, the y component is 1 as well. And so the unit vector is going to be the vector v over the magnitude of vector v. So the magnitude of vector v is going to be equal to the square root of the x component squared plus the y component squared. And so we'll get the square root of 2. And so if we go ahead and find the unit vector here, we're going to take these components, the vector v components, and divide them by the magnitude, square root of 2. So we'll end up getting the unit vector equals 1 over the square root of 2, and also 1 over the square root of 2. So now let's go ahead and write out the formula for the directional derivative. So d sub u, this time we have g, the function g in terms of s and t. So that is going to be equal to, now the partial derivative of g with respect to s evaluated at the point 2, 0, which we found to be 4, times a, or the x component of the unit vector, so 1 over the square root of 2, plus partial derivative of g with respect to t evaluated at 2, 0, which was 4 as well, times b, or the y component of the unit vector, 1 over the square root of 2. So then we'll get 4 over the square root of 2 plus 4 over the square root of 2. So in this case, we can add the fractions, and so say we'll get 4 plus 4 is 8, so 8 over the square root of 2. If I want to rationalize the denominator, I can multiply by square root of 2 over square root of 2. So then we'll get 8 times the square root of 2 over 2, which can simplify to 4 times the square root of 2. And so the next set of problems are going to be about maximizing the directional derivative. And so the maximum value for the directional derivative can be found by taking the magnitude of the gradient vector of f. And so the direction in which that maximum value occurs is simply just at the direction of the gradient vector. So whatever its components are, that's going to be the direction. So for these next set of problems, let's find the maximum rate of change, or the maximum value of the directional derivative f at the given point and the direction in which it occurs. So for number 1, f of x comma y is going to equal y squared over x, and the point given is 2, 4. So once again, the maximum rate of change, or the maximizing the directional derivative, can be found when you take the magnitude of the gradient vector f. So let's go ahead and first find the gradient vector f. Now remember, in order to find the gradient vector, we need to have the x and y components, and so the x component is f sub x, and the y component is f sub y. So let's go ahead and first find f sub x, or the partial derivative of the function with respect to x. Now if x is treated as a variable and y is the constant, I can go ahead and rewrite y squared over x as y squared times x to the negative first, because now I can use the power rule. So when I use the power rule, the partial derivative is going to be negative y squared times x to the negative second, or negative y squared over x squared. And so if I go ahead and evaluate it at the point 2, 4, we will then get negative 4 squared, or negative 16, over 2 squared, which is 4. So we'll get negative 16 over 4, which is negative 4. So now let's go ahead and find f sub y. So in this case, y is the variable, x is just going to be a constant. So we have 2y over x as the partial derivative. And so let's go ahead and evaluate it at the point 2, 4. And so we'll get 2 times 4, which is 8, over 2, which gives us 4. And so if I were to rewrite the gradient vector function here, the gradient vector f is going to be equal to, well, the x component is f sub x, which we found to be negative 4 when evaluated at the point 2, 4, and the y component is f sub y evaluated at the point, which we found to be 4. And so now let's find the magnitude of that gradient vector. So the magnitude is obviously the square root of the x component squared, so negative 4 squared is 16, plus the y component squared, and so that we get the square root of 32, and we can simplify square root of 32 into the square root of 16 times the square root of 2. Square root of 16 is 4, so we can simplify it into 4 times the square root of 2. Now the maximum rate of change of f, or the magnitude of the gradient vector, we found to be 4 times the square root of 2. And so now in order to find the direction, remember the direction is the same as the components of the gradient vector evaluated at the point. So we've already found the gradient vector evaluated at the point to be negative 4, 4. And so that is going to be simply the direction of the maximum rate of change. So now for number 2, we have f of x and y equals sine of x times y, and we have the point 1, 0. So first let's go ahead and find f sub x and evaluate it at the point 1, 0. So f sub x, if x is the variable, y is the constant, so derivative of sine is going to be cosine. We keep the inside function the same, and then we multiply by the derivative of the inside function. So partial derivative of xy is just simply going to be y. So then we're going to get y times cosine of x times y. So now if we evaluate it at 1, 0, we get 0 times cosine of 0, which is simply 0. And so now let's go ahead and find f sub y. So this time y is the variable, x is the constant. So the derivative is cosine of xy. keep the inside function the same, times the derivative of the inside function, so derivative of x times y would be x. So then this time we will get x times cosine of x times y. So if we go ahead and evaluate that at 1, 0, we'll get 1 times cosine of 0. Cosine of 0 is 1, so 1 times 1 gives us 1. So the gradient vector in its component form is going to be f sub x, which is 0, and then f sub y, which is 1, both evaluated at the point 1, 0. So now the magnitude of the gradient vector is how we find the maximum rate of change of f. So this is going to be the square root of the x component squared plus the y component squared. The square root of 1 is just 1. And so that's going to be the maximum value. And the direction in which it occurs, remember the direction is going to be the same as the gradient evaluated at the given point. And so that is going to be at 0, 1. And so the next set of questions are going to be about finding tangent planes, or the equation of tangent planes that are tangent to surfaces that have functions with 3 variables, so x, y, and z, and finding the normal line to the given surface using symmetric equations. So given a multivariable function that has 3 variables, x, y, and z, and a point which has the coordinates x0, y0, and z0, the formula for the tangent plane to the given surface at the specified point is going to be f sub x evaluated at x0, y0, and z0 times x minus x0 plus f sub y evaluated at x0, y0, and z0 times y minus y0, and then plus f sub z evaluated at x0, y0, and z0 times z minus z0 equals 0. Now in order to find the normal line, you just need symmetric equations. So the formula for the symmetric equations are going to be x minus x0 over f sub x evaluated at the point, so x0, y0, and z0 equals y minus y0 over f sub y evaluated at the point x0, y0, and z0, and then that will equal z minus z0 over f sub z evaluated at that exact same point. So for this problem, we have to find the equation of the tangent plane to the given surface at the point, and then find the normal line to the given surface at the same point. So for number 1, we have x squared plus 2y squared plus 3z squared equals 21, and then the point is 4, negative 1, 1. So let's go ahead and first, before we do anything here, we need to get everything to the same side of the equation. So I'm going to go ahead and subtract the 21. So we get x squared plus 2y squared plus 3z squared minus 21 equals 0. And then we're going to eliminate the 0 and set it equal to the multivariable function. So now we can set it equal to f of x, y, and z. So now let's go ahead and find f sub x. So f sub x, the partial derivative of f with respect to x. Now the derivative of x, or x squared, is going to be 2x, plus derivative of 2y squared is 0, derivative of 3z squared is also 0, and derivative of negative 21 is also 0, because we're only deriving with respect to x. And so now if we evaluate it at the point 4, negative 1, 1, notice there is no y or z variable. There's only the x variable, so 4 times 2 gives us 8. So now let's go ahead and find f sub y, or the partial derivative of f with respect to y. Now y is the variable, everything else is a constant. So derivative of x squared is 0, derivative of 2y squared is 4y to the first, derivative of 3z squared is 0, and also derivative of negative 21 is also 0. So we get 4y, and let's evaluate it at 4, negative 1, 1. Notice the x and z values, there are no x and z, so it's only negative 1 that we plug in for y. So 4 times negative 1 gives us negative 4. And so finally, let's find f sub z. So if z is the variable, everything else is a constant, so the derivative will be 6z to the first. And then evaluating it at 4, negative 1, 1, there are no x and y values, so 6 times 1 will give us 6. So once again, the equation of the tangent plane is going to be f sub x evaluated at the given point, which we found to be 8, times x minus x0. Now the x0 comes from the given point, So the given point has the coordinates x naught, y naught, and z naught. So x naught will be 4 plus f sub y evaluated at the point, which is negative 4, times y minus y naught. So minus a negative 1 will be plus 1. Then plus f sub z evaluated at the point 4, negative 1, 1, which we found to be 6, times z minus z naught, so z minus 1. And that will equal 0. So if we go ahead and simplify, we get 8x minus 32 minus 4y minus 4, so distributing all these numbers here, plus 6z, and then minus 6 equals 0. So we get 8x minus 4y plus 6z equals, so now negative 32 minus 4 is negative 36, negative 36 minus 6 is negative 42. If I go ahead and add that to the other side, we'll get a positive 42. And so now to simplify with one more step here, I can go ahead and factor out a 2 from the equation, so we'll get 4x minus 2y plus 3z equals 42. If I go ahead and divide by 2, then we'll get 4x minus 2y plus 3z equals 21. And so that's the equation of the tangent plane. So now in order to find the normal line, all we need to do is write out the formula for the symmetric equation. So once again, it's going to be x minus x naught is 4, over f sub x evaluated at the point 4, negative 1, 1, which we found to be 8, which equals y minus y naught, so y plus or minus a negative 1, which is plus 1, over f sub y evaluated at the point, so negative 4, which also equals z minus z naught, so z minus 1, over f sub z evaluated at the given point, which we found to be 6. So those are going to be the symmetric equations, which is the normal line to the surface at the given point.